In quantum computing, perfection is the goal, and Oxford scientists just set a new world record for it. They built a quantum logic gate so precise, it makes a mistake only once in every 6.7 million operations. This shatters their own previous record and marks a monumental leap for the field. To put it in perspective, this gate is more reliable than the odds of being struck by lightning in your lifetime. Such reliability was once a distant dream. Now it's proven in the lab. This breakthrough means building a truly useful quantum computer is no longer just theory, it's an engineering reality. Quantum computers are delicate. Their qubits are easily disturbed, leading to errors. For years, scientists have fought to suppress these errors. Oxford's achievement shows errors can be reduced to almost unbelievable levels, opening the door to longer, more complex quantum algorithms. The previous error rate, 1 in a million, was impressive, but not enough for practical machines. Now, with 1 in 6.7 million, we're much closer to fault-tolerant quantum computing. This is the threshold where a quantum computer can correct its own errors faster than they occur. It's like moving from a shaky prototype to a reliable, high-performance machine. This milestone signals the era of practical quantum computing is drawing near. Oxford's new record isn't just a number, it's a fundamental shift in what's possible. The future of quantum computing just got a lot brighter. How did Oxford achieve such precision? Their secret combining trapped ions and microwaves.
Instead of transistors, their quantum computer uses a single calcium ion, held perfectly still by electric fields. This is their qubit. Holding the qubit securely is the first step to reducing errors.
The real breakthrough is in how they control the ion. Traditionally, lasers were used, complex and hard to scale.
Oxford switched to microwaves, the same waves in your phone, but controlled with extreme precision. Carefully timed microwave pulses perform the logic operations.
Microwaves are reliable, easy to miniaturize, and can be integrated onto chips, making the system more stable and scalable. No need for bulky lasers or complex optics.
They even achieve this at room temperature without heavy magnetic shielding. This makes the technology practical for real-world use.
Imagine building a quantum computer on a silicon chip, with millions of microwave emitters controlling qubits. This leverages decades of semiconductor progress.
By proving microwave control can be more precise than lasers, Oxford has paved the way for large-scale quantum computers. The future of quantum hardware is electronic, scalable, and robust.
Why does a low error rate matter? It's all about quantum error correction. Qubits are fragile, so errors are inevitable.
Error correction codes need lots of extra qubits to protect a single logical qubit. High error rates mean thousands of physical qubits for just one reliable qubit, making quantum computers huge and expensive.
But as error rates drop, the number of extra qubits needed plummets. Oxford's new record dramatically reduces this overhead.
Fewer qubits means smaller, cheaper, and more practical machines. Less power, simpler cooling, and easier engineering.
This transforms quantum computing from a massive experiment into a technology that could fit in a much smaller space.
High-fidelity operations mean researchers can focus on scaling up and developing new algorithms, not just fighting errors.
This breakthrough changes the economics of quantum computing. It brings practical, accessible quantum technology within reach. The path to real-world quantum computers just got shorter.
One precise qubit is great, but we need millions working together for real power.
Oxford's high-precision gate is a crucial foundation. Each quantum calculation requires a long sequence of gates. If any fail, the result is ruined.
Think of it like building a skyscraper. Every brick must be strong. Oxford's bricks are now incredibly reliable.
This gives engineers confidence to design much larger systems. A promising approach is modular, many small, precise processors linked together.
Each module must be nearly perfect for the network to work. Oxford's low error rate makes this modular vision viable.
With reliable modules, scaling up becomes a matter of connecting more units. This is how today's supercomputers work, and it's the future for quantum machines. The era of large-scale networked quantum computers is within sight. Oxford's breakthrough is the blueprint.
Oxford's precision also enabled a world-first teleporting a logic gate between two quantum processors.
Scientists have teleported quantum states before, but never a full computational operation.
Imagine two processors, Alice and Bob. You need their qubits to interact, but they're far apart. Oxford used a photonic link and quantum entanglement to teleport the gate's function from Alice to Bob.
This is essential for distributed quantum computing.
Gate teleportation is the quantum glue that lets any qubit interact with any other, no matter the distance. It unifies separate modules into a single, powerful machine.
Oxford's success in both precision and networking tackles the biggest challenges in quantum computing. They're building both the high-quality components and the connections between them. This integrated approach is key to scalable, powerful quantum systems. The future of quantum networking is here. Oxford is leading the way.
Single qubit precision is a milestone, but two-qubit gates are the next big challenge. These gates create entanglement, the heart of quantum computing.
Two-qubit gates are much harder to perfect. Current error rates are far higher than single-qubit gates.
A quantum algorithm is only as strong as its weakest link. The high error rate of two-qubit gates limits what we can solve.
Perfecting these gates requires delicate control between two quantum systems, an immense challenge.
Scientists worldwide are racing to close this gap. The goal: bring two-qubit gate precision up to single-qubit levels.
Oxford's microwave control method puts them in a strong position. Success here would unlock truly fault-tolerant quantum computers. The next breakthrough could be just around the corner. The race is on. These breakthroughs aren't just academic, they're paving the way for technology that could change everything. A large-scale quantum computer could solve problems impossible for today's supercomputers.
Imagine revolutionizing drug discovery, materials science, finance, and AI. Quantum computers could design new medicines, develop better catalysts, and help fight climate change.
They'll also transform cryptography, breaking old codes but enabling new, unbreakable quantum-safe encryption. The same principles powering quantum computers will secure our digital future.
Oxford's work is laying the foundation for this future.
The pace of progress is accelerating. We're moving from scientific exploration to engineering a new kind of machine. The quantum revolution is underway. The world is about to change.